is firstly to describe the screw as a mechanical device, secondly to identify its physical attributes and its functions in surgery, and thirdly to outline the techniques for insertion in bone. After studying this guide, you should be able to identify the basic screw forms and sizes of the AO armamentarium and outline the principles underpinning the surgical techniques of using screws to achieve a variety of outcomes. Asked the question, what is a screw? Surprisingly few can describe a generic screw's basic function. All these are screws: aircraft and ships' propellers, a corkscrew, and surgical screws. What have they in common as mechanical devices? A screw is a device for converting rotational forces into linear motion. Due to the helical morphology of the thread, as it turns in a material, the slope of the helix causes the screw to move along the longitudinal axis of its shaft. With the exception of some corkscrews, a generic screw has a solid central core, about which is wrapped a helical surface. In the surgical context, most screws have a screw head, the function of which will be described later. One of the basic attributes of surgical screws is the material of which they are made. Most are metal, either stainless steel or titanium, there being inert, or virtually inert, in the body tissues. Of course, biodegradable screws are made of a variety of materials that are not inert in the body tissues, as they are designed to be absorbed slowly. Some screws are threaded throughout the length of their cores, fully threaded screws. Others are only partially threaded over a portion of the core furthest from the screw head, so-called partially threaded or shaft screws. They were also referred to as lag screws in the past, but the term lag is now reserved for describing the function of a screw, not its thread form. This slide uses as an example the thread of a screw designed to gain a hold in cortical bone, a cortical screw. A surgical screw is a device manufactured to high specifications and is to be used with care and precision. In order to select the correct instruments and technique for insertion of any screw, the surgeon needs to be familiar with its dimensions. The symbol of a circle cut through with a slash represents diameter. The diameter of the core determines the minimal hole size for the screw to be accommodated in the bone, and so determines the drill used to create the pilot hole for the screw. The outside thread diameter, as illustrated, determines the minimal size of any hole through which the screw will glide without the threads purchasing in the bone. This is sometimes known as the nominal diameter of the screw, as the screws are often named by this dimension. For example, the standard cortical screw has an outside diameter of 4.5 millimeters and is called a 4.5 cortical screw. The effective thread depth is the maximum depth of the helix theoretically available for gaining purchase in the bone, and thereby driving the screw forward when it's rotated. It is half the difference between the core diameter and the outside thread diameter. An appropriate length of screw needs to be chosen. Too long, and it may cause problems by irritating the soft tissues or protruding subcutaneously. Too short, and it will not gain full purchase in the bone. The techniques of measuring the correct screw length will be considered shortly. The pitch of the screw is the length traveled by the screw with each 360-degree turn of the helix. The shorter that distance, the finer the pitch. The longer that distance, the coarser the pitch. The finer the pitch, the more turns of the helix engage in a given depth of cortex. The screw head has two functions. One is to permit the attachment of a driver in order to produce the necessary rotation. This is achieved either by slotting the head, as in wood screws but no longer in surgery, or by producing a shaped recess. This is usually hexagonal, but may be a crosscut or a star shape. The second function of the screw head is to arrest motion when the head contacts the surface of the bone or plate hole, or washer, which is effectively a one-hole plate. For this reason, the diameter of the head must be greater than the outside thread diameter. To introduce a screw into a firm and relatively unyielding material, such as cortical bone, certain steps are essential. A core diameter pilot hole is drilled. As already described, this is determined by the diameter of the core of the screw. For example, the core diameter of a standard cortical screw is 3.1 millimeters, and so a 3.2 millimeter drill bit is used for the pilot hole. If the screw is inserted so that the head will directly contact the cortical bone surface, the bone is countersunk to receive the head. This will be discussed shortly. A female thread then needs to be created in the cortical bone to accommodate the male helix of the screw thread. This female helix has to be an exact reciprocal of the screw thread in terms of pitch and outside thread diameter. The female helix may be created by using a dedicated tap in the pilot hole or by using a self-threading or self-tapping screw. The self-threading screw has 2 or more flutes at its tip, specially designed both to cut an accurate thread by removing cortical bone and to avoid jamming of the resultant bone debris in the helix. As indicated, the selection of the correct length of screw is vitally important. For a standard cortical screw, the tip should just project beyond the far or transcortex, so that the thread bites in the full cortical thickness. For the self-cutting screws, the length must be chosen so that the flutes pass clear of the transcortex. If they lie within that cortex, bone can grow into the flutes and make their later removal difficult. So measure the screw hole for length and add 2 millimeters. How does tightening the screw create compression? When the screw is driven fully in, the head contacts the underlying bone and resists further longitudinal motion. If the screw is then rotated a fraction further, tightened, the threaded portion tries to advance, and this creates a minute stretching of the screw, resulting in a tensile force in the core. This is balanced by an equal compression force at the screw head bone interface. Why should we countersink the cortex beneath the cortical screw head, the cis cortex? You will recall that stress is the force applied divided by the area over which the force is applied. The smaller the area, the greater the stress on the bone. If we fail to countersink the cortex, the area of compression is small and the stress high. This risks failure of the bone. If we countersink, the area is increased and the stress reduced. It is to be noted that, with cancellous screws, which are used largely in metaphyseal and epiphyseal sites, the underlying cortex is too thin to countersink. If we try to countersink, the head compresses the cancellous bone beneath, and it may fail, being much less resistant to high stress than thick cortex. What we do in that case is not to countersink, but to use a washer, which increases the area over which the screw head compression is borne, thereby reducing the stress. If we insert a screw across a fracture plane with a view to closing the fracture gap and applying a compressive force at the fracture plane, there are certain conditions to be met. If we thread both the near, cis, and far, trans, cortices, the compression will not pass across the fracture plane. This can be seen in the polarized light model, where the force lines generated by the grip of the screw threads in the fragments, plus the compression forces generated by the screw head in the near fragment, are visible. In this model, the threads have been prevented from purchasing in the near fragment by drilling a gliding hole at least the diameter of the outside thread diameter. The head then generates compression forces which can be seen to pass across the fracture plane. This is known as the lag screw technique. The standard AO cortical screw has an outside thread diameter of 4.5 millimeters and is therefore referred to as the 4.5 cortical screw. Its dimensions are shown on this slide. The head diameter is 8 millimeters. To accommodate the core, a 3.2 mm pilot hole has to be drilled. If it is to be used for the lag technique, the gliding hole is made with a 4.5 mm drill bit. The thread is cut using a 4.5 cortical tap. The screws are available in stainless steel or titanium. The smaller cortical screw has an outside thread diameter of 3.5 mm and is therefore referred to as the 3.5 cortical screw. Its dimensions are shown in the slide. To accommodate the core, a 2.5 mm pilot hole has to be drilled. If it is to be used for the lag technique, the gliding hole is made with a 3.5 mm drill bit. The thread is cut using a 3.5 cortical tap. They are available in stainless steel or titanium.